Alright, so starting off the notes for 1.6, we have parent functions. We are going to be matching up the basic parent functions A through H with the graphs. I suggest that you pause the video and give it a try. And then after you give it a try, we'll go through one by one. Alright, so I'm going to start off with some of the, I guess, easier or more predictably obvious. If we have this graph right here is a parabola, so that matches up with x squared. So that's going to be c. And then we have next to it, and we've seen that these this year, here's an x cubed. I'll go ahead and cross this one off. X cubed is h, so this one matches up with h. We have f here, pick the f of x equals x. That's the same as y equals x, so for every x value, whatever x is, y is the same. 1, 1, 2, 2, 3, 3, and so on. So this would be f of x equals f. Yeah. And then let's see, for this one, the first one, f of x equals c, that means no matter what x is, c is going to be the same. It's a constant. So f of x equals 4, for instance. No matter what our output's of 4, in this case it's an output of 3. So this is a horizontal line which matches up with that. So we have a here. The square root function right next to it is a sideways parabola. Used to a parabola like this. If we had a plus or minus, then the parabola would be about the x-axis, just like x squared, its inverse is about the y-axis. So this would be root x. And note, for all these, we could always do an input-output table as well. For this graph right here, absolute value, that means all of our outputs are going to be its distance from 0 or positive. So if we look over here, the 1 absolute value is 1, 2 absolute value is 2, absolute value of negative 1 is 1, absolute value of negative 2 is 2. So this would be g. D right here is the step function. Don't worry about that. We're not going to do that this year. And so that remains 1 over x, which is an inverse or rational function. So that would be e. And as x increases, y decreases. So we see as x is increasing in value, moving to the right, y is going down in value. So those are the matching up of our parent functions, and what we're going to be doing within this section is just matching up graphs, doing some basic graphing of transformations. We'll get more into detail with the transformations as we move forward. As I indicated earlier, we are not doing step functions this year, so you can disregard this on your notes, and we'll move on to piecewise functions. Up here, again, step functions. We're not doing step functions. We can go ahead and cancel those out. For piecewise functions are called piecewise functions because they're basically broken up into pieces. And if we go back to our functions definition, or our first functions example, which was time and temperature, x is our input of time in that example, and f of x is our output of temperature. So what a piecewise function, and we did briefly cover this in terms of just plugging in values into a piecewise function, but now we're going to graph, is saying when our time is less than -1, this is how we determine our temperature from -1 to 1. That's how we determine our temperature. And if we are greater than 1, that's how we determine our temperature. So I think the best way and the easiest way to go about this is doing simply an input-output table. So for this graph, what I'm going to do is start at the key point at -1, and then go less than that. So at -1, what I'm going to do is substitute in -1, plug it in for there. So 2 times -1 is -2, and -2 plus 3 is -1. So at the input of -1, we have an output of -1, which gives us the coordinate -1, 1. Note, I have it as a closed circle because it's less than or equal to. Note, for piecewise functions, typically they write the inequality or domain in which we're graphing the piecewise function in inequality form rather than interval form, but both could be done. Then we want to graph values that are less than or equal to -1. So instead of, if I'm over here on my graph, I want to go to less than values. So I'm going to pick on an input-output table, and you'll see I'm just deciding to do this in my head. If you want to write out the input-output table, you can do that as well. I want to move to the left. I don't want to move to the right because we're only graphing this first part when it is less than -1. So I'm going to pick the next value of -2. So I'm going to take negative 2 and plug it in for there. So if I 2 times negative 2, that'd be negative 4. Negative 4 plus 3 is negative 1. So my coordinate is negative 2, negative 1. We also recognize that this is a line. This is a linear equation right here. So once I get 2 points, I can graph from there. And you see that we're graphing it off to negative infinity. So you just graph as accurately as possible, like so. The next part, we are graphing from negative 1 to positive 1. So I'm going to start off with negative 1, plug it in for there. And you see there is an error in my notes here. Well, we'll see actually. When we plug in negative 1 in for here, negative negative turns positive. Positive 1 plus 4 gives us 5. So negative 1 comma 5. Over here on the graph, negative 1, 5 would be up here. And we note that we can't have two outputs for one input. So we are going to get rid of just this inequality sign. I'm just going to highlight it, indicating no, it's not there. So it should have been, that's a fallibility on my part with the notes, that should be negative 1 less than x. Of course, I could have taken it off of here, but just like you see here at 1, this one's greater than equal to, and this one's greater. It's whatever the problem gives you in terms of which one is equal to. And note, it could not give you one that it's equal to on both of them. So for instance, negative 1, it could be a less than here, or x greater than, or negative 1 less than, and this could also be a less than without an equal sign. That's okay. We don't need an output at every input. So when, again, when I plugged in negative 1, when I plugged in negative 1 in for here, whoops, I didn't mean to do that. We plug negative 1 in for x here, we got 5, so negative 1 comma 5 is our coordinate. So we go over to the graph, negative 1, 5 would be right here. And then we see it's a line again, but how about we get one more point at the minimum? So I plug in 0 in for here. 0 plus 4 is just 4, so that would be 0, 4. And we want to graph it to the x value of 1, so that's going to be right here. I know that because rise over run is negative 1, and we have a y-intercept of 4. So if I start here and I go down 1 over 1, we would get to here. Note, I could have also gotten that from plugging 1 into x here. Negative 1 plus 4 gives us 3. So that's that part of the graph. And note, this is an equal sign, so I do have a closed circle right here. Next part, if you notice, that's a quadratic. In any case, we're just going to plug in values. First, I'm going to plug in 1 in for there. So 1 squared is 1. 9 minus 1 is 8. So I'm at the point 1 comma 8, and that's an open circle. Okay, not the best, but you get the idea, hopefully. If we plug in 2 in for x, since we're graphing greater than, I'm just picking nice, neat values again. If I plug in 2, that would be 2 squared is 4. 9 minus 4 is 5. So I have 2 comma 5, which is right there. And it's a parabola, and that graph so far is kind of like, I don't know what that looks like. So maybe let's plug in one more value, 3. I'm going to plug 3 in for there. 3 squared is 9. 9 minus 0 is 0. So I get 3, 0. And if I plugged in 4, I would be like negative 5. And so it'd be like this. So hopefully you're seeing that this is kind of the extreme part of the quadratic. And if you notice 9 minus x squared, that's we haven't done translations and reflections yet. We'll do that next section. But it's a transition up 9 and a reflection about the x-axis, so therefore it'd be a parabola that has a vertex right there, and it's going like this, but of course we're only graphing from there. Let's give a shot on one more. So now we have a quadratic and a radical. Again, doesn't particularly matter if you recognize what parent function is. Our goal is to just do an input-output table. So we're going to start off with 0. I'm going to plug 0 in for x here. So I have 0 minus 1 squared. 1 squared is positive 1. And I have 1 minus 1 is 0. So at 0, we have an open circle at 0. So 0, 0. And it's an open circle because we have a less than symbol. We also want to get more values other than just 0, and it's less than, so I'm going to go to negative 1. So I'm going to take negative 1 and plug it in for here. If I plug negative 1 minus 1, that'd be negative 2. Negative 2 squared is positive 4, and I still have that negative out there, so 1 minus 4 gives us 3. Negative 1, comma, negative 3. I'm not sure if I said that right, so negative 1 in for there gives us 2. 2 squared is 4. 1 minus 4 is negative 3. So again, we have -1, -3. -1, -3. Plugging in -2 in for here, -2 minus 3 is -3. -3 squared is 9. 1 minus 9 is -8. So I'm going to come down to -2, -8. And we see, hopefully, that this is the bottom part of a parabola. If we go back to our rows of translations, this would be a parabola, basic parent function shifted to the right one. This would be an up one. And then it's also flipped over the x-axis, so it looks something like this. So that is an accurate graph. If you're unsure, again, on the translations and reflections, which we're covering later, you can simply use the input-output table. Next, we're going to plug in 0 in for here, so that doesn't work, right? 0 minus 2 gives us root -2, which we're not graphing imaginary numbers. First x value that would work would be +2, so if I plug in 2, I get out 0. And that's a closed circle, if I saw that correctly. Yes, it is a closed circle because we have the equal. Now, for radicals, it's nice to square root perfect squares. So we want outputs of, I'm going to do this actual input-output table. We want outputs of 0, 1, 2. And I think if we get 3 values, that'd be enough. We already had this one. That'd be 2. So what we want to do is ask ourselves, what would I need to plug in for x in order to get square root of 1? Because square root of 1 equals 1. I'd have to plug in 3. Note if I plugged in 3 into there, 3 minus 2 equals 1. Square root of 1 is 1. If I want to get out 2, I need the radical to be 4 underneath. So what do I need in for x to get out 4? And that would be 6. So let's just check again. If I plug in 6, I get 6 minus 2 is root 4. Root 4 is 2. Note that just makes them nice and neat. If you want to plug in whatever, like 2, 3, 4, that's totally fine. You're just going to have decimals. So you'll get the same graph either way. So I'm going to zoom out here. We have 2, 0. Already have that one. 3, 1. And then we have 6, 2. And there we have our graph. So that's all we have for this section. Hope you have a great weekend. Have this 1.6 homework in by Sunday night. And I will see you all on Monday.